Testing, testing. Okay, and we're live. So today we are going to be looking at paper. This paper is called One Shot Implicit Animatable Avatars with Model-Based Priors. This is a relatively recent paper coming out earlier this month. A couple different groups here. You have Zhejiang University, you have Max Planck Institute, and University of Cambridge, and Xiaohongshu Inc. Xiaohongshu is a social media and e-commerce platform. It has been described as China's answer to Instagram. Would have thought that WeChat would be the okay, Oni. Okay, so it's basically Alibaba and Tencent are the behind it. Okay. So they do have a nice little website where you see the nice little GIF, abstract, videos. Very nice looking. It's basically animatable nerfs with just from a single human. Quite impressive. There is some artifacts you can see when they spin around. All the like generated back. The back of the face tends to kind of look like the back of a head, which is weird, but cool stuff. I think it's interested to see what how they make animations within a nerf. Cool. So let's get started here. So neural rendering methods for creating human avatars typically either require dense input signals or leverage a learned prior. Propose elicit, a novel method for learning human neural radiance fields from a single. Okay. So they have two priors that they're going to be using here. They're going to be using 3D geometry prior and a visual semantic prior. So priors are refer to a prior distribution. So in statistics, one of the first assumptions you have to make when you're looking at some data is maybe assuming a certain shape for this distribution. Usually that means a Gaussian. You're saying, what do I expect the distribution of this data to be? And you can say it's a Gaussian, in which case your prior is a Gaussian. So that term has kind of expanded and kind of is now used to refer to assumptions that are made about the kind of distribution or maybe some specific part of the problem that allow you to constrain the solution in such a way that you can come up with something that's a little bit cleaner, more closed form, or even works in the first place, right? A lot of times you need these priors. So, for example, convolutional neural nets, people call that a translational invariance prior, where you're basically saying that a dog in the top corner of the image is the same thing as a dog in the bottom corner of the image. So that's a little background on what a prior is in case you didn't know that. And here they have two priors, 3D geometry and visual semantic prior. We'll expand on what those are specifically. So this is the prior for the 3D geometry, is basically saying they're assuming that a human is a human, and there's elbow bones and knee bones and foot bones and so on. And the visual clothing semantic prior, it's the second part here, uses clipped-based pre-trained models. Okay, interesting. Segmentation-based sampling strategy that locally refines different parts of the avatar. Okay, and then they use a variety of data sets here: ZJU mocap, humans 3.6 mil, and deep fashion. We'll put that in green, which is our data set color. And then they have code will be public for research purpose. Creating realistic 3D contents of animatable human avatars from readily available camera inputs is of great significance. AR/VR application. I would say it's more so than AR/VR, just all digital content in general. Yeah, human-specific neural rendering methods right now, they have a couple links here to previous work, but in general, you need dense and well-controlled inputs, right? So whether that's multi-view videos or long monocular videos. So monocular just means one camera, but long as in you would, it's a very long in the time dimension. Sometimes inconvenient to obtain such high-quality, dense inputs. Here they have some other work, Arch and Arch++. Human-specific nerfs. Instead of learning conditioned models from real data sets, recent works introduce various regularizations on geometry appearance. So these are the two priors, and those priors guide optimization. So here we have the contributions in the introduction here. At the end of the introduction, now relatively standard to put a bulleted list of the contributions you are doing with this paper. So they have their illicit model, which is an animatable neural radiance field. Have a clip-based semantic prior, and then a simple-based geometry prior. So SMPL, or simple, is like a bone structure for humans. So it's originally a data set that someone made. Simple human animation. Yeah. So it's basically a standard 3D format for humans that has some specific bones, right? You have bones for elbows. You don't really have the bones for the hands, but then they have the ability to kind of map meshes to those bones as well. So it's kind of a standard. There's a lot of different ways to represent a human and animate a human. And different kind of bone structures, and when I mean bones, I mean animation bones. So, basically inside of a 3D character, there'll be these little bones like this that basically define what all the joints are. And there's a bunch of these formats, right? And simple is one that the computer vision community and has been using more and more, and just kind of is a standard. So glad to see that they're using that. Quantitative, and qualitative comparison. That it consistently outperforms. This is very subjective, so we'll see whether they can actually be for that. Okay, so they animatable human neural rendering. They have a couple split it up into 2D based methods and 3D based methods. So in 2D based methods, you have explicit temporal constraints, optical flow, warping fields. Most single image 3D based methods learn encoder decoder models. Okay, Arch and Arch++, which is the one that they mentioned here. Data-driven methods depend on extra human-specific training data and are likely to encounter generalization issues in the wild data. Yeah, I mean, I would say the first part of this sentence is a little bit extra. I think that, right, they're using CLIP here, and CLIP is trained on basically the entire data set. It's contrastive language image pre-training. So extra human-specific training data, I think some of the stuff that they're using is going to use human-specific training data. I think the generalization issues in the wild data is more interesting. A lot of times these data sets, such as mocap, human 3.6, deep fashion, they're limited to specific looks. Like I know one data set that people use all the time in this kind of animation stuff is like pictures of human or animations of humans doing thing in a room. I think this is, if we actually go to their website, we can see one of these. Yeah, here, Humans 3.6. So Humans 3.6, it's 3.6 million different animations, but in reality, it's always this same exact room. And the problem with that is that the model kind of overfits to the red carpet and the white background and this particular camera angle, so that if you take anything that's trained on Humans 3.6 million and then you try to extend it outside of that, it's not going to work as well, right? The generalization capability of anything trained on this type of data set is not going to be great, because if you have a human with a blue carpet from a different camera angle in a different kind of lighting condition, it's not going to work as well. So that's kind of what they're referring to here with generalization issues in the wild data. Okay, a couple different 3D based methods here. Setting of novel view synthesis from only a single image is challenging for NeRF-based methods because incomplete geometric information. A conditional generative NeRF that generates, that is conditioned on something. SynNeRF and Diet NeRF use pre-trained image encoders. I mean, a pre-trained image encoder is the same exact thing as a clip-based visual semantic prior. They're just using different wording there, but ultimately they're going to be using clip for the same thing. Oh, or maybe not. Maybe they're not actually using the pre-trained clip model. Maybe they're just using here they're referring to clip as a learning method. So maybe they are copying clip, but not actually using the pre-trained clip. But I doubt that. I suspect they're probably just using the pre-trained clip model to get image features. Okay, clip-based lost as a regularization on the nerf. Okay. The turf, like a latex nerf. Clip-based image similarity. I think this should be a comma. Mono NHR. Yeah, this is what we were talking about. Limited generalizability. Quite an English word there, because of a biased distribution of training data sets. The wrong color there. Why don't we let's do pink for errors in paper. Formulate our task of creating free view videos for a character as follows. Okay. Now we're going to start defining some terms here. So we have a single view image, I of S. Let's use blue for definitions here. With camera parameters E sub S, simple parameters beta and theta sub S. Beta is going to be the body shape of the character, and then theta sub S is going to be the body pose of the character. So then you have a motion sequence of length N, sorry. Simple pose parameters fancy theta, where theta sub S is the pose, and then you have some pose over frames from I equals 1 to L. Camera parameters for each frame. So E sub T here, these are the camera parameters. Again, the same sequence length here. You have I equals 1 to capital L. And output is N video frames. You have the video frames, which are also of the same length. Okay. Capital I sub T, superscript I. So this is the video frame at time T. Is, I think that's capital gamma. Yeah, capital gamma. Capital gamma of F of X, F function here, which is, I think they're going to grab it here. F is a pose-conditioned radiance field function. And then gamma represents volume rendering. So neural radiance fields, right? You're representing a, usually a signed distance function, or here they're saying a radiance field function with a neural net, right? So this is the the neural net that takes the x and the theta, which is the camera, the simple pose, so the pose of the human, and then x, which is, I guess, the image. What is x? X might be the input image. And then it renders it creates basically a radiance field, and then you can use that radiance field along with the camera parameters, which is basically just the pose of the camera. And the pose of the camera and that neural radiance field, you use a volume rendering technique, right, such as ray marching or something like that, and then that'll give you your actual image from that pose. Okay, so preliminary simple, which we looked, actually the word for, or what simple stands for, is skinned multi-person linear model. This is a skinned vertex-based template model driven by large-scale aligned human surface scans. Okay, so skinned vertex-based template model. So this is, model here doesn't refer to like a machine learning model. It refers to like a 3D model. Vertex-based template, so I think they're probably referring to the vertices of the mesh that is outside of the skeleton. And skinned, usually in animation, refers to kind of, there's this mapping between, go back to, yeah. So there's this mapping between each of the little vertices in this human, these human models, and then the bones. So, right, you want the, for example, the elbows and the pit of the armpit. If you don't have a good kind of mapping function that maps the deformation of the mesh to the movement of the bone, you'll get these kind of animation bone artifacts. Artifacts, armpit. Not using the right word, but like something like this, right? Where you see here where the neck joins, like that's not how it would actually look in real life, right? The deformation of your like flesh whenever you move your joints is different, and it's difficult to capture. So Simple has a way to kind of do that more cleverly and more accurately, right? Okay. Simple encodes posed body shape by a pose parameter. So this is 72 dimensional here. So let's use blue color here. We have 72 dimensional. That's how many different numbers you need in order to fully encode a human in the Simple system. And that's the pose, and then you have a shape parameter, which is 10 dimensional. So pose parameter and then your shape parameter. So in total, you have 82 numbers. And with those 82 numbers, you can perfectly get a 3D model of a human, which has 6,890 vertices, right? So you don't need to specify the position of each of those 6,890 vertices as long as you specify this pose parameter and the shape parameter. Simple does the rest for you. Nerf is a human-specific variant of a neural radiance field, which supports free view rendering of a moving character from monocular video inputs. Human nerf represents a moving character with a canonical appearance volume f sub c. Okay. Warped to an observed pose to produce output appearance volume f sub o. So f sub o, which is a function of x and p, where x is a position, and p is the pose parameters, right? So output appearance volume, which is a function of the position and then the pose, is equal to the canonical appearance volume, which itself takes as a function the motion field. So this motion field maps positions in observed space back to the canonical space. J is 3D joint locations, and omega here is local joint rotations. Okay, so you're basically doing all this like warping between different spaces here, right? You have joint space, have the space of each individual vertice. You have 3D joint positions, local joint rotations. You have this canonical appearance volume, output appearance volume. So there's a lot of kind of mapping back and forth between these different high dimensional spaces that represent an animated human. E sub t is the transmittance of the light. R is the pixel ray cast from the observer. So this is how NeRFs work, basically. I think we've covered this before, but when you're doing a NeRF, you're effectively casting rays. This image is the one that I keep going to, but a NeRF represents there's a 3D volume that it's representing, right? So inside here, inside this cube here, inside this voxel, you have a representation of this little Tonka truck. And that representation is not in 3D space, it's inside the weights of a neural network, right? This F sub theta here. And when you give F sub theta a camera position, right? X, Y, Z, and then a kind of a look angle, right? You can think of it as basically a ray. So you're saying, I'm here in this position, I'm looking at this exact point here and this direction. And then the neural radiance field, right, parameterized by this neural network, will tell you at each point within this volume what the color and, for example, density or transparency is at that point. So that is the ray here, this ray. And if you want to create a full 2D image, right, 128 by 128 pixels, for example, you would have 128 by 128 total rays. And for each pixel, you could say, what is the ray that goes through this pixel? And then let me get the value of the color and the density inside the NeRF volume for each ray. What they call here the pixel ray cast. Okay, so CLIP is a visual language pre-trained model trained on 400 million diverse image text pairs from a massive web scrape. CLIP is a really great piece of technology because not only is it kind of one of the largest vision language models out there, but it's also MIT licensed. So yeah, this is the big part here, is that you can use CLIP for commercial use, private use. So a lot of times, like these big models, right, even something like Stable Diffusion, there's this kind of user license agreement that you have to agree to, and there's all this stuff, and people can get sued, and it just kind of leads to people not using it. But whenever they made CLIP, they were very clever, and they decided to use an MIT. I don't know if clever is the right word. I would say generous. And that means that now everybody uses CLIP as their kind of feature encoder, where you can give it any image, and then CLIP will turn it into a little vector for you, a little feature vector, latent space vector, an embedding, whatever terminology you want to use, but that little embedding is much lower dimensional than the image, but also encodes kind of the semantic meaning of the image. Model consists of an image encoder. We have an image encoder E sub I, and then a text encoder E sub T, which are both transformer-based models, right? The clip learns a joint embedding space of text and image by pulling the embeddings of paired images and pushing unpaired ones apart. So this is the this is what the contrastive part of the clip acronym stands for. Contrastive means that it's kind of an unsupervised learning method where you don't need labels, right? You don't need labeled data. This isn't a supervised learning method. What you're doing is you're basically just taking things that are similar and then having a loss function that puts those together in an embedding space, and then taking things that are different and then pushing those away, having a loss function that pushes those away in this embedding space. And if you do that over 400 million images from the internet, over time, this embedding space will kind of have a lot of semantic meaning in it, where two things that are close in this embedding space are very likely to be semantically related. All right, now we got the first big figure here. Very cool looking, impressive figure. Method overview. Our method takes a single source image of a person to generate an animatable avatar, which can be applied to generate pose-guided free view renderings of the person animated by any target motion in simple format. So here, simple is a format. Implicit trains animatable implicit human representation of human nerve by one-shot prior-based learning. Produce two model-based priors to guide the optimization. Simple-based human body prior and the model-based semantic prior. For the human body prior, we first use a multi-view video frames rendered by simple, so this is A here. Simple mesh initialization. Initialize the post-condition geometry of the implicit representation. Okay, so you have some animation, right? Video in simple format, which means that for each of these pictures, you have not only the full mesh and pose of the human, but you can also get these masks here. And then B, a silhouette loss is used to constrain, so that's here, is used to constrain synthesized geometry and body poses. So because you have the full mask for these simple animations, right, you can get basically the trace, right, the mask or the silhouette, as they call it here, of the human at that point in the animation, right, at that frame T. And then you can use that to kind of craft a loss over that. And then C, a segmentation sampling strategy is used to refine body part details. Okay, so what is going on here? So these here are cropped parts of the original single image input. So this is the only picture that they have of this guy, right? And then they're doing segmentation-based sampling to refine. Okay, so I think the segmentation here, zoom in a little bit, it refers to this. So the simple format, right? Not only does it allow you to get the full pose for each frame of an animation, and then the mesh, which allows you to get a 2D mask But because you also know the full mesh, right, those 6,000 vertices, you can also segment the mesh into the different parts here. So you have kind of the upper arm, the lower arm, the body, the torso, the legs, and so on. And they're segmenting that part out, right? So then they can have segmentation sampling just for one leg, just for the other leg, and so on. I wonder how they're... Right, like I wonder if they're segmenting the input image. How do they get the correspondence for those? But see, they'll describe it for sure. Okay. That's the first part here. This is a simple based human body prior. So this is all the information that they're kind of extracting from this simple. Then you have your visual model-based semantic prior. So the flow here is like this. It's it's not left to right, left to right. It's like you go from the input image, you have your simple-based prior, then you have your visual model-based prior, finally get the animatable implicit representation. So let's see what they have here in the visual model-based prior. You have pose view consistent semantic loss. So what does that mean? Or the semantic prior plays an essential role in one-shot learning, which provides D, pose view consistent semantic supervision, or novel views of novel poses with a powerful pre-trained visual model. You have a pre-trained image encoder, right? That's your clip. Then you have ground truth view, which is, I guess, just the input, single image input. Have your volume rendering function gamma here. And then you have your training view. So notice how these little cameras here, they're all just camera positions. And then you combine the neural radiance field with the camera position and the volume rendering function here, you can get an actual image, and then that image gets fed into an image encoder, such as clip, and then you get your image embeddings here, or your latent vectors, right? And because clip is trained on so many things, it kind of has good meaning there. And okay, so basically it seems like what they're doing is that you have your input pose, which is your human, and then you have all your novel poses, right? So you're starting to map this human into all these different simple poses in the animation that you have. And then this loss here, what it's saying is basically saying that the image embeddings that come out from your input image should try to be as similar as possible to the image embeddings that come out at each frame of this animation, right? What they're calling the novel poses. So you want each frame of this animation should have a similar clip embedding, right? If you took each frame of this animation and then fed all of those images into clip, you would expect all those latent vectors to be close together, right? Because you're looking at the same human being. So this is kind of a regularization loss that basically tries to make sure that the human is always the same. That's kind of how you get the background. But that's also, I would say, why you get some weird artifacts. So like if you actually look at this, right, notice how this view here, the back of the head, is particularly weird, because the way that this clip kind of loss is going to function it wants the human to be the same at every time, right? So like if the front of the shirt has something, clip is going to put that in the back of the shirt, right? And you can actually see it here, right? You can see how this guy here, he's wearing this black jacket, and then you can see his gray t-shirt through the black jacket, right? And because you're using this clip to kind of enforce this consistency in the semantic meaning of the human, right? Like once you actually get the back, you're getting an artifact, right? It's not going to just have the whole back be the black jacket. It's going to try to make the same thing, which means you have this black and then you have this gray in the middle. That's also why you see artifacts of like a face in the back. Like the back of the head almost looks like a head, like a face. There's a couple other artifacts here. Like, see some points just kind of floating outside of the person's space. Okay. Prior-driven one-shot learning for single image-based human rendering. Figure 2 illustrates our overall pipeline. Per subject optimization. What? Right, so you're going to be running this for every single. You give it a single image of the person that you want, and then there's this process is going to run. So you have to basically train it per human. This is not something that you train on 10 humans and then it just like works with every other human. I have here character pose and camera parameters, training view. This is the input view. So where are they getting this input view? That's kind of what I was wondering here, right? So whenever you have here input pose, right? Maybe that's what they have here, estimated simple parameters. So at some point, you have to estimate, right? You have to say this human right here, this image that I have, here is the corresponding simple pose for it, right? So at some point, someone's guessing what the position of this camera is and what the simple pose for this human is. So wonder how they did that. Reference view. Rendering a consistent input view. This is their reconstruction loss. So basically, one loss that they use here, there's a variety of different losses here, but like one loss that they use here is that if you're using the if the train here, the V reference position is the same as the V train position and the input view, then the images should be the same. So you can go through this whole pipeline and then render the human at this input pose, and you should end up with the same image, right? So you can just use your mean squared error or input image and then training image, or like image after you've gone through this whole pipeline. So this is just mean squared error between those two images, and then you have also this LPIPS, which is the VGG-based perception loss. So VGG is a ConvNet actually. Quite old at this point. Yeah, so VGG loss is a type of content lost introduced by blah, blah, blah. VGG loss is based on the ReLU activation for a pre-trained 19-layer VGG network. So it's similar to kind of what they're doing here with the clip pre-trained image encoder, where you feed a bunch of images into clip, and then you're saying each of the latent vectors that come out of these images should all be the same because you're all looking at the same human. This VGG-based perception loss is basically a similar idea, where you're taking two images and you're feeding them into this, VGG, probably the biggest one they can. So VGG 19, I would think it might be the biggest one. It's a pre-trained image encoder, and then they're saying the vector that you get for each image when you feed it through VGG should be the same for both images. So maybe they use this perception loss. I don't quite remember why, but maybe it's like it's shaped nicely, right? So these losses, like, you can think of them as like the hill, right? And the analogy of the neural networks as this marble rolling on a hill, right? And you want it to find the like low points of the hill. These loss functions, sometimes these hills are very like kind of jagged, right? And there's lots of like little mini holes, and it's like basically it's very hard to like roll the marble on this hill. So you want to have losses that are very kind of smooth, and then these hills kind of are very good for kind of very naturally rolling the ball into the local minima that you want. So loss shaping, the way to describe what I'm trying to get to there with my analogies. But that could be a reason for them using this VGG-based perception loss. Another reason could be that they want to compare their results to future or previous work, and previous works were using these losses. But I would say that the difference between the clip vectors is probably more meaningful than the difference between the vectors that come out of a VGG pre-trained encoder. Okay, so here they say the different things that they want. They want a consistent appearance with the input character, a plausible geometry, and a body pose that matches the target motion. So there's kind of three different high-level losses, and all the different losses and optimization that you're doing is kind of with respect to that. Contrast, learn prior, 3D scan. Have their two priors here. There's actually two visual model based semantic priors. There's the clip, and then there's also the VG. So two different pre-trained encoders there. Visual model based semantic prior. So ultimately, they want minimizing the embedding distance between the synthesized novel views and the input views. So what we keep mentioning here, that you want these little latent vectors that come out of the clip to all be the same. So one kind of failure case for this is if someone was wearing a t-shirt that had one kind of design on the front, but then on the back it had a different design, this method would kind of like fail very much for that, because basically the view from the back, right, when you fed it through clip, would produce a very different vector from the view from the front. So there's this kind of like underlying prior that a human from every single view should produce the same latent vector when fed through an image encoder. Right. Different views of the same person should be significantly closer than those of a different person. Okay, so clip-based cosine distance as the semantic loss. You have your loss based on the distance between the clip embeddings. I have iTrain is the rendered image in the sampled training view, and iref is the reference. And then here you have phi is the normalized embedding function. IT, so basically just clip. And here, this capital T here is just transpose. So you're basically taking this vector that comes out here, right? The latent representation. You put the image into clip, you're going to get a vector. You put the other image into clip, you're going to get a vector. If you take the dot product of those vectors, right, you can, if that number is very big, that means those vectors are the same direction. If that number is very small, that means those vectors are not the same place. So this like roughly tells you, or multiplying the dot product of those two is basically a rough way of getting how close those vectors are. Okay, so here is how they get the actual pose for the input, right? Off-the-shelf pose estimation models. Multi-view renderings of the meshes are used as pseudo-ground truth. M-view camera poses and template meshes generated by Simple. Right, so these are the images up here. Where if you have an animation in simple form, you can just kind of pick a mesh for it and then just actually render the images and you'll get the full images for it. So here they do mention that, right, the clip embedding is going to be similar, but it's not going to be perfect. This is the masked silhouette loss. Is itself a combination of an MSE loss and then a one-way chamfer loss. Have your silhouette mask S, and then you have a alpha map A. This is the element-wise product. You take your S of that pose, so the silhouette of that pose, and then you have the alpha map at that pose. You have the squared difference between those for all poses, or for the pose in S. Why there's a sum here. Oh, maybe it's all pixels. Edge S computes the edges of the mask. Yeah, and AP is the pixel value of A at P. So this is for all pixels in the image. This constraint maintains the character's pose and target motion during training. Clip loss enforces global semantic consistency. Right? You want the vectors that come out of those to be the same. Okay, and then they're not patch-based similarity loss. So in order to kind of, I guess this is another prior, right? At the end of the day, this is another human assumption that they're using, but they're basically saying that the similarity of different patches be the same. Is a way to kind of do this better. So like, for example, here, rather than putting the whole human through, they're doing it in these little patches because that allows you to kind of maybe get a slightly better semantic loss here. So this left foot should be the same as the left foot. The head should be the same as the head. So you're doing the head separately from the foot. It seems like they get better results with that. They mean here by this patch-based similarity loss. Shows the training camera to render a local patch for the body part. We can also crop a corresponding reference patch from the input by the simple set. So this is like they keep kind of referring to the fact that their input image has a representation problem, or has the estimated parameters. So there's a little bit, I don't know, there's a little bit of kind of overstating here, right? They keep mentioning that one of the best part, or the best part about their paper is that they only need a single image as input, but then there's this step here where they basically assume the simple pose for the input. So they're really not just using the single image as the input. They're using a single image with the full pose, right? And then they're just saying that the pose is close enough that it doesn't matter. So like this entire approach is, you need to know what the pose of the single image input is, right? So there is something there where this whole approach only works if you have the a good estimate of what the pose of the input image is. Right? I would say, like, if you're going to be doing that anyways, then just put the constraint on the input image, right? Rather than saying, hey, you can give us any image, and then we will just kind of estimate what the pose is for that image, and then use that pose as if it were the ground truth for your input image. Just ask people to give you two poses, right? Ask people to say, give me an input image forward and then backwards, or you from the back. And then if you use that as the kind of input images and you have two, and then you also have the corresponding poses for them because you ask the person to pose in that position, I think you'll get significantly better results, especially for the kind of back where you have to imagine it. And that's actually here what they're referencing, the Yanis problem. So the Yanis problem is this problem, the fact that the back of the human like kind of is being forced to look like the front of the because of their reconstruction losses, or because of their semantic consistency losses. Okay, they do some tricks here where they select a reference view from the left rear or right rear direction. Here are the different data sets that they use. We have ZJU, mocap, mill, and deep fashion. The single image inputs are sampled from the first camera of ZJU mocap and the third camera of Human 6. And then deep fashion is basically high resolution body photos. I have a couple different baselines that they're going to be comparing to here. They have neural body and AnyNerf. They have neural human performer, NHP. All three methods use simple-based human body priors, right? So they're all using the same simple format. And then these are the metrics that they're using. Peak signal to noise ratio, PSNR, and structural similarity index, SSIM. I mean, I don't know, those are a little bit hand wavy. And the perceptual similarity metric, LPIPS, is also kind of hand wavy. So I would say that some of these previous works, they're not using this LPIPS metric, you know? So using this obscure metric LPIPS and then also putting it in your loss function here is kind of cheating, because now you're pushing gradients into your model that optimize this LPIP when the things you're comparing against don't use that kind of, aren't using LPIP. So then you're saying, wow, ours is better in perceptual similarity based on LPIP, but that's because that's literally part of your loss function. I think it would have been more honest if they didn't use LPIP and then they didn't put LPIP in their loss, but then they used it in evaluation. Yeah, I mean, I think this is really what you want to be looking at, right? Like, don't bother looking at these, right? These charts here, because all these numbers are kind of nonsense anyways. PSNR, SSIM, LPIPs, like, those aren't actually going to capture the quality of the image. I think this is really the images you want to be looking at, right? Where they have their input image, and then they have PFU, Pamir, these are other kind of approaches of doing this, and then theirs. And you can see the difference here. So one thing I'm immediately noticing here is, for example, here with this guy with the tank top here, you have PFU is actually quite good about the back of the head, right? Look at the way that the back of the head doesn't look at all like the front of the head. That's quite good. Compared to their work, the image is a little bit crispier, a little bit clearer, right? It's not as fuzzy as these two previous ones, but you have this kind of like Yanus problem happening where the front is really trying hard to look like the back. But where they're good is, for example, here, these like boots, PFU makes these look terrible, right? This Pamir also makes them look terrible, but in theirs, the boots actually, I mean, they don't look perfect, but they look a little bit better. So I don't know. I wouldn't say it's significantly better. I would say that it's on par and it has its own problems. Okay, here they have some ablation studies. So you can see without the different things here. So they have without the semantic loss, right? So this is the clip loss. Without body part refinement. So body part refinement is the part where they're basically taking little crops of the individual body parts like the head or the leg, and then using those and doing the semantic loss specifically on those little subsections. So you can see without the semantic loss, you kind of get this kind of like averaging here, where it's like you don't get the hard edges of the tank top. It just kind of like makes the whole back just kind of the average color of this. Without geometry constraint, hard geometry. So this is the simple geometry, right? So the fact that you know what the full pose is for the simple, that as the constraint, and then here the difference. Without simple mesh initial. I think that's this part here. Estimated simple parameters. So that's the part that we said is a little bit cheating. So when they remove it, you actually see the result is basically nonsense. So, contrast to matching the simple geometry directly by a hard constraint of silhouette loss, we penalize the silhouette misalignment only in turn. I think they're saying that because the simple mesh here is a naked human, it doesn't necessarily map exactly to the shape here, right? Like this guy wearing a hat, that head is not going to look exactly the same as kind of the silhouette that you get from the bald head of the simple mesh, right? Like the fact that the beanie has like a weird like nub at the end of it. That's part of what they're saying here. That making this loss not super hard allows clothing and affiliate objects to kind of bet it better. Okay, interesting, nice. Okay, so they don't just use clip. They compare with a couple different other image encoders here. So they have Dino VIT. They have a VIT is Vision Transformer. They have a VIT pre-trained on ImageNet, and then a large VIT, and then a small clip. So then they have a smaller clip. This is a great picture right here. This is showing you the difference of different image encoders, right? So clip is just significantly better, right? And I feel like you can use this as reasoning just in your own projects, right? If you're doing a computer vision project and you don't know what kind of pre-trained image encoder you want to use, I think you just look at this picture and instantly you realize that kind of this large clip is the best, right? And the fact that it's MIT licensed, even more so. So I think for my next project, I'll definitely be using clip. Rich pre-training data and a large model capacity are key factors, the effectiveness of a semantic loss. They just summarize the paper. So this paper introduced Elicit, a novel method to construct an animatable implicit representation from a single image input and generate a free view video of the character in the target mode. Cool stuff. Have different. So for NVIDIA, Tesla, V. Quite familiar. Randomly decide whether to sample from a novel view. Novel 0.5. Okay, so like some kind of augmentation. All the images are 224 by 224. Yeah, enhance the versatility of our one-shot training framework. I think this to me is like multiple images. The like T-pose shot of the front and the back of the human like if you use the same approach with that, I feel like you get really good results, and it would solve a lot of these kind of like problems that they were running into with the Yanis problem with the back of the head looking weird. And I think asking people to take a front and a back shot would actually be fine, right? But cool. That was one-shot implicit animatable avatars with model-based priors. Thank you for watching the stream, and see you tomorrow.